Okay, good afternoon, ladies and gentlemen. Again, my name is Beta Yu. I'm calling in from Midas, and today we're hosting a seminar through Michael Baker for a particular bridge project that C.Y. Young from Michael Baker has done. Today's topic is going to be covering the modeling and analysis of a new Kentucky Lake Bridge. This structure is actually a basket handle network tied arch bridge. So he'll be discussing some of the major challenges he has faced, as well as some of the complications that he was able to overcome. All material you see in this presentation is copyrighted by Midas as well as Michael Baker. So please, if you have any questions or you are curious about some of the presentation details, please contact us before, just for the information that you do see. Today's seminar is going to be done by C.Y. Young of Michael Baker. He is from the Lexington office in Kentucky. As you can see, he has his bachelor's degree in the University of Technology in Malaysia and has his Master of Science in the University of Kentucky. Okay, I do see that some people are saying they cannot hear me at the moment, so we'll do a quick sound check again before we begin. Please, if you could hear me, please indicate to the hand icon that you can hear me. Okay, seems like everyone can hear me, and it is actually the Louisville office. I apologize. Okay, so everyone can hear me. Okay, so we'll begin again. A couple projects he has been participating and part of, as you can see here, is the 320 Egner's Ferry Truss Bridge, the I-64 over the Ohio River, the Milton-Madison Bridge replacement, as well as the Turnpike Authority for New Jersey sign replacements. Before we begin, a couple things that we have done internally is we've been doing a couple sessions for the engineers who have registered for this particular C.Y. Young presentation. The session indicates because his project was based on a steel truss bridge, we have shown engineers who have participated into our seminar how to do these steps with Midas Civil before we actually showed the presentation with C.Y. Young. This is something that we are replicating on a monthly basis on various different bridge projects and bridge structures. So as of this month, because the presentation was regarding a steel truss bridge, the modeling was done for a truss bridge, same with the analysis as well as the design. We have a three-part session going on. The last session, part session 3, was done last Thursday to complete the 3-session interval. For next month, Daniel Baxter will be presenting another bridge structure on load rating, so we will be covering and showing the engineers who are interested how to do that portion as well. So if you have any questions, at the end, we have our contact information at the end, so if you have any questions regarding it, please give us you could email us at any time. So another thing that we are focusing on is because we are going to be talking about Midas Civil, a lot of engineers have requested for information regarding the Civil software itself. So to briefly give you an example of what Midas Civil is and what we do, Midas Civil is a software, 3D finite element software that helps with the modeling, analysis, as well as design of all structures. So if you are in this criteria where you do the modeling, analysis, or any design for any bridge structures, our software is a perfect tool to assist you with the engineering work. It is not something that we ask for you to replace all work with, but something as a complementary supplement to what you are doing. If you are interested with Midas Civil, if you follow the link above to northamerica.midasuser.com for Bridge Midas Civil, you will be able to download a trial version of our software. It is a 30-day activated license. These are the instructions below. Again, I know that it's really hard to kind of do everything right now, so at the end I have inputted the web address again over again. So if you have any questions at the end, please take a look at this, and if you are interested, email us and we'll be able to help you directly, and one of our representatives and consultants will be able to give you a call to help you along with this. So now what I'm going to do is I'm going to bring this presentation over to C.Y. Young, and he will begin his presentation on the modeling and analysis of a new Kentucky Lake Bridge. So we will begin shortly, and please, if you have any questions, type them up in the questions tab, and he will, at the end of the session, he will do a quick Q&A session for about 5 to 10 minutes to take any inquiries that the consultants engineers would have. So please hold your questions until the end. However, if you do have immediate questions, we do have some of our consultants on standby to answer any technical issues with the GoToWebinar problems. Thank you. CY, you haven't made the presenter now, so if you begin, you could bring your presentation. Okay, CY, your volume was off. Can you start over again, please?
Can you hear me?
Yes, we could hear you now.
Okay. Again, what I'm going to talk about today is the topic of the modeling and analysis of the new Kentucky Lake Bridge of the which is the 550-foot basket handle network tie arch bridge. So today's webinar learning objective is to understand the modeling of the tie arch bridge, which includes the advanced analysis. So we also will learn how to use Midas built-in features more efficiently, and which will reduce the time and the frustration during the finite element modeling. Let's go through the presentation outline quickly. I'm going to talk about the project overview of the Kentucky Lake. Then we will go through several different models, like the static arch model, RWDI iteration model, the merged arch model with a local complex model, the static hanger loss analysis, followed by the arch global stability analysis. So where is the Kentucky Lake project? It is located at the western part of Kentucky and provides a vital access point to the land between the Lakes National Recreation Area. So our client, Kentucky Transportation Cabinet, KYTC, will actually be replacing 2 of the bridges with identical tie arch bridge over Kentucky Lake and Lake Buckley. The Kentucky Lake crossing was awarded on December 2013, and Lake Buckley crossing will be advertised a year later, which will be end of this year. Here's the aerial view of the Kentucky Lake Bridge. This bridge actually represents a major investment in Kentucky transportation infrastructure. It's actually one of the longest bridges in the Commonwealth, Kentucky, which will be the landmark for the area. The new bridge will replace the existing structurally deficient and functionally obsolete Angus Ferry Bridge, as you can see on the top of the screen. The existing bridge is actually only 2 lanes, 23-foot wide truss bridge. On the other hand, the new bridge is 75-foot 4 inches wide, carries 4 lanes of traffic with 10 foot of multipath or sidewalk across the lake on the US 68 and Kentucky 80. Kentucky Lake Crossing is total of 9,080 feet long, including a widening of 2,400 existing causeway, and also the 580-foot lagoon bridge, which is actually not shown on the screen. The west approach span is about 1,400 feet long, followed by the 550-foot tie arch bridge and 1,650-foot long of the east approach span. Both west and east approach span are continuous span welded steel plate girder. The general public and the Citizen Advisory Committee actually determined the signature structure to be the basket handle tie arch bridge for the main span. Well, what is the tie arch bridge? In general, tie arch is an efficient long span structure, and as we know that the tie arch imposes the horizontal truss because of the curvature of the compression ribs. So the load path of the bridge starting out from the bridge hanging down from the hanger, and it ends up with the truss coming down to from the ribs to the knuckle and resolve themselves in the vertical component that goes down to the bearing. And the horizontal forces will be carried by the tie girder. So why we pick Midas Civil as our final element program? Well, because the Kentucky Lake tie arch bridge is a long span complex bridges. We need to build a rigorous 3D model for the bridge, for this project, to determine the demand and also to analyze a complex component of the bridge. So Midas Civil is a very user-friendly and has an Excel-compatible table features that will increase the modeling pre- and post-processing efficiency. It also integrates with the various different advanced analysis tools, such as the moving load, construction stage, eigenvalue, buckling, and nonlinear analysis. Midas Civil is also equipped with a simple and convenient graphical user interface. Later introduction to the modeling. So for me, I always ask myself, what is the purpose of the model? What we try to accomplish and what we try to get from the model. We always start simple in the modeling. We always do 2D, model to then evolve into more complicated model. It's easy to debug in a simple model than debugging the complex model later on. It's also important to understand the program's capabilities and limitations, what the programs can do and what the programs cannot do, so that we need to make certain assumptions in our analysis. I always have the modeling checklist, which has the 4 primary items. The first one is the geometry of the model. The second is section and material properties of the model, the boundary conditions, and the last one is loading. It serves as a reminder to be, and also a step-by-step input into the model. The last is to perform various testing and study, and it's always good to do a simple benchmark problem so that you get familiar with the program and understand the analysis that we try to do later on. So speaking of this point, we did a lot of design studies and analysis for the Kentucky Lake project during preliminary design phase. The first study that we did is to look at the network hanger versus vertical hanger on the tie arch bridge. The study demonstrated that the maximum live load demand on the tie and rib using network hanger system is 40% of the using vertical hangers. The numbers you look at right now doesn't necessarily represent the actual live load demand that we use for the final design of the bridge, but it's a one length of HL93 applied to the bridge for the study. just for comparison. The second study that we did for the Kentucky leg is look at the integral flow system versus floating flow system. Basically, integral flow system is a string of frames into the flow beams directly, while for the floating flow system is string sitting on the bearing and connected to the flow beams. The integral flow system offers several benefits, such as it eliminates the string of bearing and joints from future replacement, while it also imposes a challenge to the deck system because it introduces a creep and shrinkage force from the deck to the stringers and to the connection, and introduce the lateral bending stress to our floor beams. However, the cost is much lesser to use the integral flow system compared to the floating flow system because of the maintenance and inspection of the bearing, the stringer bearing. And finally, we selected the integral flow system for our final design of a Kentucky leg bridge. We also look at different span to rise ratio, varies from ratio of 4 to 7, as you can see on the screen. We also look at the incline angle study by looking at the lateral stability of the bridge, eigenvalue, and mode shape of the bridge with different incline angle. The last study where we did is to look at the multi-use path. Because the Kentucky leg bridge is very close to the Ken leg resort part, the need of the bypass was amplified. But we are looking at whether to place the multi-use pipe inside or outside of the arch. So using Midas Civil allowed us to input pedestrian live load on the model. So it would generate the maximum live load effect to the bridge by doing both study, by doing model inside and outside of the bridge. We selected the multi-use path inside the bridge because it's preferred by our client to allow future widening of the lane load, the live load, to become 6 lane of live load. So after multiple testing, study, and experiment, as you can call it, the simple model finally become and evolve into a final 3D arch model. So the final geometry of the Kentucky leg bridge is 550 foot long from center line of bearing to center line of bearing. It is 94 feet wide from center line of the tie to center line of the tie. And it's 110 foot tall on the 15 degrees inclined plane. So on the final 3D arch model, we model everything as a beam element except the deck of the superstructure and the footing as a plate element or shell element. We model the hanger as a truss element, which I will explain later why we're doing it. Here are some of the screenshots from the final arch model. So the final arch model is a linear model that allows us to do static analysis and allow the load superposition, which is preferable to facilitate the member design. Because we're doing the linear model, we have to check the hanger, which model as a truss model, to make sure that the assumption elastic modulus that we made is always true or valid to be used. The Midas allow the user to assign the individual load case, which is very helpful because if there's any changes to the load in the future, it can be updated easily. Few examples that Midas allow user to input different types of the loading. First is the plate pressure load, which will apply as a future wear surface on the deck. Midas also allow the user to input the nodal loads, which we use it, in this case is the approach band bearing load. And the screen on the right showing that Midas allow user to input the beam element beam load, which we use as to apply our RWDI wind load to the model. In this final arch 3D model, we also do the construction stage analysis to simulate the real-time constructions. On Kentucky Lake Bridge design and analysis, we assume the tie arch bridge is constructed on land and float in. We also include the deck pouring sequence in our construction stage analysis to check that, make sure our hanger doesn't go slack, and also that to check the hanger assume elastic modules to be true and allow us to use the load superposition later on. We also apply the time-dependent load in our construction stage analysis, which is the creep and the shrinkage load. So these four figures show the construction stage that we assume in our analysis. It started with the substructure constructed on the first stage. It follows by the float in of the arch. And next is the planar pull of the deck. Then the last construction stage is the closure pull and the deck overlay. Once the construction stage is analyzed, it will become the post-processing model for the moving load analysis. The moving load analysis in Midas is very useful because it can place the live load on the bridge to generate the maximum or minimum live load effect on the members. In Kentucky Lake, future 6 lanes of live load were used, which include the future widening of the bridge. 4 strike lane live load is used for hanger loss analysis and also the tie fracture design. I'm going to talk about the hanger loss analysis later on. Midas has the capabilities to allow users to scale up and model different live load that is not included in the live load library of Midas. Another helpful feature is that it allows users to convert the critical live load to static load case. For example, we are interested on the critical forces of one of the member of the arch. Let's say it's on this middle of the bridge tie location. So Midas we can use the Midas live load tracer to show us the live load pattern that generate the critical live load case. And then we can convert this live load pattern to a static load case, which is very helpful to us to use it for our advanced analysis. Baker retained RWDI to conduct wind engineering study on Kentucky Lake Bridge. And we are required to provide the structure mass and eigenvalue analysis result to RWDI for the wind buffeting analysis and the wind tunnel study. So Midas is capable to perform eigenvalue analysis, and the dynamic results can be easily extracted in the table format from Midas. Because leg bridges is supported by deep pipe paths and waterline cap, we do the substructuring between the deep foundation and anything above. The deep foundation will show its model on another program. So we have to do iteration between these two programs to come out with the converged 6x6 stiffness matrix. Then we provide this information back to RWDI to finalize their wind tunnel study. Then RWDI will send us back the RWDI wind load, static wind load, to be applied in Midas model. There are a total of 28 load cases of RWDI wind load that we need to apply into the model. And the last step is to compare the deformed shape and the deflection magnitude for the 28 load case with RWDI, with what provided by RWDI, to make sure that the result and the load applied is valid and it's come out to be comparable. Then we extend our modeling effort to develop the local and shell model to analyze and look at the critical section of our bridge. Midas has the capability to import CAD file and convert it to a finite element model. And actually, it's very helpful because different people can develop separately the model and merge into the model later on. So one of the most critical sections for an arch bridge is the knuckle, so which is located at the intersection between the tie girder, rib, and end flooring. A knuckle is a highly stressed area complicated by the geometry of it for fabrication. As you can see on the left is the drawings of the knuckle, and the right is the knuckle Midas model. Another section we are interested on is the tie hanger location. These two sections will merge into our arch model, which I have shown previously, and we analyze the model to get the demand from the merged model, and compare with our hand calculation. This really increases our confidence in the complex member and the connection design. So in order to connect the local plate shell model to our beam model, we use a transition element called a spiderweb link. The spiderweb link is actually a beam element which is very stiff flexually, but with a moment release or pin at the plate elements, and thus preserve the rotational continuity without applying in-plane bending on the plate elements. The link is very soft axially and allows the Poisson effect in the plate elements without over-constraining the member and create force stresses. We impose the limit of the detail model using engineering judgment and by applying St. Venin principle, which means that the boundary condition is set at least a girder depth away from the area we are interested to look at. So we design the knuckle by checking the effective stresses or permissive stresses of the element. by imposing Von-Mises U criterion. It can be seen that the higher stress originates from the ribs and flowing through the knuckle plate and to the bearing, shown on the left side of the screen. We also use the model to check the shear stress of the knuckle and diaphragm effective stress. Here's a screenshot of the diaphragm effective stress that we used to design our diaphragm. Another local model that we built is to check the connection design of the hanger to the ribs. So we perform nonlinear material analysis to predict the connection stresses. Here's a quick animation of the analysis. Next, I'm going to talk about the static hanger loss analysis. The hanger loss or hanger exchange is analyzed in accordance with the PTI recommendation for static cable design, testing, and installation 6th edition. So here are the cable loss and cable exchange load combination. For cable loss is 1.1 DC plus 1.35 DW plus 0.75 live load and impact, and plus 1.1 factor of the cable loss dynamic forces. I will explain what is the cable loss dynamic forces on the later slide. But the live load that we use in the cable loss is actually the full live load placed in the strap length, which is a full strap length for Kentucky leg bridge. The cable exchange is using 1.2 DC, 1.4 plus 1.4 DW plus 1.5 live load and impact, and also the cable exchange force. But the live load used in the cable exchange is actually at least one length of the live load shifted away from the cable under exchange. So for Kentucky leg, we use the full length of strap length of live load for the cable loss, and 2 lengths shifted away for the cable exchange load case. There are 3 basic steps to perform the static hanger loss analysis. First step is to apply the dead load to the base structure with all cable intact, which we call it as a System 1 model. We can use the construction stage model to capture the dead load of the structures. It is also followed by apply the live load to the same base structure with all cable active. This is how the Midas use the post-construction stage model and apply the live load on it. The last step is to take the maximum dead load and live load of the hanger from Midas and multiply with the dynamic factor of 2 and apply in the opposite direction of the original cable tension force with one of the cable removed. And we call this model as System 2. I mean, pictures tell better than 1,000 words. So on the first model is a System 1 model, which is the base structure with all cable active. So this is basically represent the construction stage analysis model that we've done that capture all the dead loads of the arch. Then the second is basically you can use the same model with the live load applied on the bridge. Then the System 2 model is to obtain the cable loss dynamic forces. So basically it's by removing one cable from the System 1 model and apply the dead load plus live load, and with the 2.0 dynamic factor applied on the opposite directions where the cable is removed to get the system 2 forces. These two, the forces are then superpositioned, and it becomes a static hanger load combination that used to design the component of the arch. As shown on the figure at the chart, as you can see that the cable loss introduce large in-plane moment to the ribs and tie. I mean, this is one by removing one of the hanger of the load case, and it needs to be done for all the hanger on the arch. The last analysis I'm going to talk about today is the global arch stability analysis. One of the objectives is to perform the stability analysis is to ensure the arch does not buckle globally before the yielding of the structures. We utilize two methods for Kentucky Lake project. First is the linearized buckling analysis, which also can be called as a linearized eigenvalue analysis that perform on deformed structures with consideration of the full geometric stiffness metric. This can be easily accomplished in Midas Civil because Midas Civil is built in with the buckling analysis. This analysis provides a theoretical solution for the buckling modes of the structures. The second method is a full geometric nonlinear analysis. The geometric nonlinear analysis is an incremental iterative procedure that carry out on an imperfect geometry of a structure to compute the second order effects on the internal force. The initial imperfections are introduced directly into the undeformed arch geometry that we used to run linearized buckling analysis previously. The shape of the imperfection is applied to the ribs and rib bracings following the first mode shape that obtained from the linearized buckling analysis. I believe the new version of Midas allowed user to convert the mode shape and apply it to the modify the nodes coordinate and to run the geometric nonlinear analysis later on the later stage. So for the nonlinear analysis, the buckling load is calculated by means of a series of subsequent loadings of the factor H strain load combination that we apply as an incremented to the maximum loading in the increment factor of 0.1 until the analysis fails to converge using the Newton-Raphson iteration method. If the load level reaches the bifurcation point, the nonlinear calculation will not find a solution of the equilibrium equation anymore. Because of that, the lack of convergence indicated that the structural load stability and the buckling mode shape could be determined from the deformed shape from the last successfully iterated state of the analysis. So when such analysis is performed, the resulting buckling factor shall satisfy the following strain limits that we use in the project, which is not really codified. We using engineering judgment and previous experience on the previous project, the limits that we use is 2.5. So the lambda, which is the eigenvalue from the linearized buckling analysis in Midas needs to be more than 2.5. As for the full geometric nonlinear analysis, the lambda is the last log steps that fail to converge. Here is the two figures that show the comparison between the two different analyses using the same strength load combination. As you can see on the screen, both deformed shapes are very comparable. Well, the lowest buckling factor that we gain from the linearized buckling analysis is more than 4.0, while the nonlinear analysis is 3.6. I want to wrap up today's presentations with a lesson learned from this project. The first lesson we learned that we always start simple in our modeling and progress into a more complicated model. We also need to understand the capabilities and limitations of the finite element program. And don't be shy to always perform study, benchmark testing to get better understanding of the program and the analysis we would like to perform. The last but not least is to remember that the one model could not do it all. Different model is used to accomplish different goals. Before I end my presentations, I just want to say thank you to our client, KYTC, our sub-consultant, Homer Engineering, geotechnical consultant, and everyone in Baker team that involved in the project. The goals were met with challenges along the way and solved by the close collaboration and support of the project team. After the completion of the bridge, Kentucky Lake Main Span will be the first network tie arch bridge in the state of Kentucky. Thank you.
Okay, for this portion now, CY, we're going to take a couple minutes for the question and answers. So if you kind of look through your questions, you're going to see people ask you a couple different questions. So if we could take about 5 minutes, 5 to about 7 minutes to answer a couple of those questions, I think that would really help them understand a little bit more about your project, okay?
Sure. And I actually can show the Midas model that we have.
That would be great too. Okay, I'll leave it back up to you, okay?
Okay.
Alrighty.
Let me go back to the screen and show really quick on the model that we have. Here is another model. It's very fine meshing, so it takes a while to just to output the graphics that we are interested to look at. Right now we're looking at the effective stress of one of the load case at the knuckle. Then this is our 3D arch model. So we have different load case apply as a static load case on the individual load case. And this is one of the models that generate the live load to be converted into a static live load. Okay, better way I could find the question. I'm sorry.
No, it's fine. If you look at on your control tab, you should see a question mark, right?
Control tab.
Or there's a questions tab on the control panel. If you expand that, you'll see a couple people have asked a couple questions. If you
I
can't,
cannot find it. I'm sorry.
okay. If not, I'll read out the questions to you, and then maybe you could just give them an answer. Is that okay?
Yeah, sure.
Okay. The first question was by Glenn Steffen. He asked, was modeling required of the structure for construction staging to confirm constructability, or is it left to the contractor?
Is actually to confirm the constructability and also the assumption that we made for the design.
Okay. Okay. Another question was, were the ribs of the model always assumed inclined, or were parallel ribs also studied?
No, it's always assumed inclined because it was selected by the public and the citizens advisory committee. So it's always inclined.
Okay. So there was no study for the parallel ribs at all?
That was done during the bridge selection process. It's a very robust bridge selection process before we even started the design of the bridge.
Okay. All right. The next question was, it appears advertiser. Okay. Was all the connection design done in Midas Civil or NFX or other solid mechanics program?
Most of the connections, well, it depends on which connection we are looking at. For the knuckle connections, we are doing it in the Midas Civil. And we also have some in-house spreadsheet to design the connections. And we use the Midas Civil as a validation or comparison to our design spreadsheet.
Okay. And did that take a very long time?
For the design spreadsheet or for the knuckle?
The knuckle within the model for Midas Civil.
The modeling, yes, it's not very that long time. If you can use the CAD and import it into the Midas, they will save a lot of time. And you can model piece by piece and merge it later on in Midas.
Okay. A couple more questions. Was the stringers designed as continuous or as simple spans?
The stringer is designed as continuous.
Okay. How is the member campering accounted in the model?
That is accounted in the construction stage analysis.
Okay.
But in the design structure plan, if the contractor choose to construct the arch differently, they will need to come up with a different camber.
Okay. I hope that answers the question. The next one is, why composite deck was used, concrete, instead of orthotropic deck?
Well, we kind of look at it, and in Kentucky prefer not to do any post-tensioning or pre-tensioning, and also by cost, cast in place deck come up to be a better solution.
Okay. I hope that answers your questions. Just to let you guys know, for the attendees, all these questions that he's not able to address and some of the additional questions that are here, he will take a look at, and then he will he'll send us a response back, and we'll send you guys the results or his answers after the session, just so everyone's questions are answered and handled. We'll take about 3 more questions. Is that okay, CY?
Yeah, sure.
Okay. All right. The next question was, did you perform any seismic analysis and design?
Yes, we did.
Okay.
But Because of the time, doesn't permit me to do it, so I didn't include it in this webinar. But we did perform seismic analysis for this project.
Perfect. Okay. And I guess you could expand on that a little bit further upon answering his questions. The next question is, are the struts necessary or can be omitted?
I'm sorry?
Are the struts necessary or can they be omitted?
Which struts?
Actually, I'm not sure. So how about we skip that one, and then maybe we could find out a little bit more in detail.
Yeah, sure.
Next was a vertical position instead of the tilted configuration considered for the tight arch?
Well, I think I answered the question previously that the general public and the Citizens Advisory Committee already determined that it needs to be a basket handle high arch bridge.
Okay. And we'll take one more question. The last question is, how do you satisfy the boundary conditions for the individual knuckle model at each stage of analysis?
We did not use the local model just to run the local model. We merged it into our 3D arch model.
Okay. All right. Guys, we're running out of time today. I want to thank C.Y. Young again from Michael Baker for this presentation. I know there's a lot of questions remaining. We will definitely address those questions post-seminar. As of right now, C.Y., I want to thank you for your participation in this today.
Thank you.
It was a very good model. I want to thank you. Going back into it. So the last thing we want to cover today is, So the last thing we want to cover is, again, at the end, if you have any additional questions or inquiries regarding this session, you could email us at midasoft@midasuser.com. So any other questions that you have that are not, that the engineers have not written out in the GoToMeeting today, you could list it out here. Again, if you are interested in trying out the program yourself, you could also indicate that in the email, or you could go straight to this website, http://northamerica.midasuser.com/bridge_civil_download trial. So here you will be able to, you will have the opportunity to give the Midas Civil a try, and it will be the full version activated for 30 days. So if you have any questions, please let me know. If not, thank you so much again for your time today. We want to invite you out to the next session. But for the meantime, I want to thank C.Y. Young again for this presentation, and I hope you guys could join us next time. Thank you.
Thank you.
Have a good afternoon, guys.